I hope you enjoyed last week's whirlwind tour of physics, but I bet that you're ready to start thinking about astronomy again. We're going to do that now. We're going to take all the tools we acquired and start applying them to understanding the rest of the universe. It seems fitting to start with our local neighborhood, the solar system. This is both because our local neighborhood is very important, it's where we live, and also because in a way we know a lot more about the solar system than about anywhere in this rest of the universe, because over the past few decades we've been able to send spacecraft, robotic spacecraft, to visit many of the objects in the solar system, allowing us to verify the predictions we had made based on ground-based observations and understanding of physics, and compare them to actual measurements. So we will be able to verify a lot of our understanding of what goes on in the sky directly. For both of those reasons, we're going to spend the next week studying the solar system. I should point out at the beginning that there are at least two aspects of the science of the solar system that I will not be able to give the appropriate time to. This includes the amazing and fascinating history of space travel and our exploration of the solar system. That will be given short shrift because we don't have the time to put into it. And the other aspect is the intriguing and exciting question of the possibility for the existence of life elsewhere in the solar system or beyond. And this is not something about which I know very much, and it's not the central focus of this class. So we will be discussing the physics of the solar system, leaving the biology aside. So with that said, what is the solar system? Well, primarily the solar system is all of the objects in bound orbits around the sun, and most of that is a star. It's the sun. To a great extent, 99.9% of the mass of the solar system is in this average-sized main sequence star we call our sun, and this star dominates the solar system in more ways than containing all of the mass. In addition to dominating the mass of the solar system, the sun extends its influence throughout the solar system in two other ways. One, we talked about last week, is the radiation, the black body radiation with which the sun glows. That is the source of our light and heat here on Earth and elsewhere in the solar system. In addition, as we'll see as part of the processes that go on in a star, the outer atmosphere of the sun is a very active place, and it is constantly emitting a stream of charged particles called the solar wind that leave the sun at high speed and propagate out throughout the solar system. We will discuss this when we talk about the sun next week, but this is a non-trivial flux of high-energy particles away from the sun, and as we'll see, it has lots of effects in the solar system. To give you a sense, every 150 million years, the sun loses a full Earth mass to this solar wind, so there is this constant stream of stuff coming out of the sun. Okay, we know about the sun. We'll discuss the sun next week when we talk about stars. What else is out there? Well, primarily what we think of as the solar system is the 8 planets. The sun is orbited by 8 large, round objects in slightly eccentric but almost exactly circular orbits of various sizes, ranging from 0.4 astronomical units, Mercury is the closest planet to the sun, all the way out to 30 astronomical units, so 2 orders of magnitude of orbital radius, all the way up to Neptune. And we see in this nice image that there's a nice cluster of very small inner solar system orbits, and then the more widely spaced outer solar system orbits, and essentially the space between the planets is mostly empty. So roughly it's the sun with 8 planets orbiting it, and the orbits are distinguished not only by being circular, but note in this image, they're almost all in a plane. So there are no planets that orbit the sun this way or that orbit the sun that way. They all orbit in the same sense, in the same plane. Clearly crying for explanation when one observes the sun as Galileo did, one notices that the sun in fact spins about an axis, and the sun's axis, surprise, is perpendicular to the ecliptic, so the sun too rotates about its axis in the same sense as do the planets. The planets themselves come in 2 very distinct families. There are the inner planets, Mercury, Venus, Earth, and Mars, the outer planets, Jupiter, Saturn, Uranus, and Neptune, and they're different in as many ways as you can think of. The inner planets are dense, as we shall see, as dense as rock or denser. They are small. This image is not to scale. The left-hand side is to scale, so that you see that Mars and Mercury are smaller than Earth and Venus. The right-hand side is to scale, which shows you that Jupiter is the largest. But between the right and left-hand side is about a factor of 10 in size. Jupiter, in fact, is 11 times as large in radius as Earth. If we put the two figures to scale, then either we wouldn't see the inner planets or the outer planets wouldn't fit. So you have to draw a very sharp line between the right and the left. The outer planets are not just bigger, they're also far less dense, and their composition is different. As we will see, the inner planets are rocky. Their composition is silicates and iron and nickel. The outer planets are mostly hydrogen, helium, and ices. And lighter elements, larger planets. Why this dichotomy? Certainly an interesting question. Okay, we have 8 planets. The solar system is not just the sun and 8 planets. There's other things floating out there. What else is there? Well, around many of the planets are objects that are captured in gravitational Keplerian orbits about the planets as they orbit the sun. They're called moons. We know of our moon. There are a total of about 150 moons in the solar system, most of them orbiting Jupiter and Saturn. But all of the planets except Mercury and Venus have moons. The outer planets tend to have many more moons than the inner planets. And some of these moons are planet-sized. Our moon is about almost the size of Mercury. Some of the moons of Jupiter are very large. Again, notice that all of these large objects, like the planets, all have the same shape. So they're all spherical. We want to understand, why is everything round? And where did these moons come from, and why do they orbit the planets and not the sun? In addition to moons orbiting the planets, there are these beautiful structures of rings. It turns out that, as we found in the 20th century, all of the giant planets have ring systems surrounding them, and we'll see that that's a ubiquitous fact. But Saturn's rings are certainly a spectacular exception. There's a reason why Galileo discovered the rings of Saturn, and it was not until the 20th century that we found the other giant planets had rings. And we'll want to understand what this structure is, where it came from, and what it tells us. Looking at the moons and the planets of the solar system, we see another property that they all share, which tells us something about what goes on in the solar system, and that is that they all seem to have suffered a little bit of damage. This image is an image of Mercury, and you see that it looks kind of like the moon, because like the moon, it's pockmarked with craters, the results of collisions sometime in its past. This image shows you that the Earth is not immune to such attacks. This famous crater in Arizona was formed by an impact only 50,000 years ago. And so there have been and are impacts onto the Earth, and this feature of cratering is one of the most ubiquitous things we see. Here's our familiar moon, this is the near side of the moon, and the familiar cratered shape of Tycho and so on shows us that the moon too has taken the brunt of many hits. Here is Ganymede, Jupiter's moon, and Ganymede too has had the impacts. What caused this? Is it still happening? Are we about to get hit? All questions we'll want to understand. So we have planets, moons, rings, something that crashes into things and creates craters. What else is out there? Well, turns out that's all the big stuff, but there are smaller objects out there. The main collection of small objects is called asteroids. This is a picture of a particularly pretty one. This is the asteroid Eros, close-up shot. And we see two things about Eros. One is that, like everything else in the solar system, it has suffered some collisions. It's cratered. But Eros is not round. It's shaped like a potato. And in general, asteroids do not necessarily follow the pattern we've seen where everything is spherical. We'll have to understand why it is that things can come in various shapes. There's this relatively densely populated region of the solar system. There's about 1/10 of an Earth mass orbiting in the asteroid belt. And in addition, for example, in Jupiter's orbit, there are these so-called two groups of so-called Trojan asteroids that orbit in Jupiter's orbit, but 60 degrees east or west of the planet, and they orbit, because it's a Kepler orbit, with the same period as Jupiter. Another thing we'll have to pay attention to. The solar system, we think, cannot possibly end at Neptune. There are objects that orbit beyond Neptune's orbit, and our best hint about them comes first from comets. Here's a pretty view of Halley's Comet from its 1910 apparition. And it turns out that comets in their cometary orbits, where they approach the sun, cannot survive billions of years. We'll talk about that later. And in order to explain the frequency with which comets are observed entering the inner solar system in the plane of the ecliptic, we conjecture the existence of a collection of objects orbiting beyond Neptune's orbits called the Kuiper belt, a disc-shaped distribution with, it is assumed, tens of thousands of objects, hundreds of which are the size of the moon or larger. Pluto would be an example of one of these Kuiper belt objects. And these are objects which, when perturbed from their orbits, form the source of the short and intermediate range comets that we see orbiting in the plane of the ecliptic. And it turns out that in order to explain the frequency with which we see comets, we can predict the density of objects that must be out in the Kuiper belt. The Kuiper belt might extend out to as much as 100 astronomical units away from the sun. Much farther away, it is conjectured that way past the orbits of the planets is the spherically symmetric halo of objects. The Oort cloud, it might have an inner Oort cloud along the disk called the Hill cloud, but these objects orbit the sun in highly eccentric orbits outside the plane of the ecliptic, and they form the source for our long-period comets. This is our collection. The first question you want to ask is, well, what's it made of? And we can answer that rather directly. The answer, of course, to what is the solar system made of is mostly the answer to the question, what is the sun made of? Because 99.9% of the mass is the sun. Of the 0.1% that is not the sun, 90% of the rest is Jupiter and Saturn. And we have here a plot of the abundances of various atomic species in the solar system, which roughly mirrors the abundance of the same atomic species throughout the universe. So when we see what the solar system is made of, we're really answering what the universe is made of. We'll come back and try to understand this later in the class, but for now it's a worthy observation. And these are the relative numerical abundances of various species of atoms, organized by atomic number. And what you need, the scale is kind of random, but it's a logarithmic scale, so that the fact that helium registers one less than hydrogen means that there's about one helium atom for each 10 hydrogen atoms. There's a factor of 10 less helium than hydrogen, and together, because everything else is down by a factor of 10,000, they comprise almost the entire content of the solar system. By mass, because a helium atom weighs 4 times as much as a hydrogen atom, that works out to about 70% hydrogen, 28% helium, and 2% the rest. Everything else is trace amounts down by a factor, as I said, of at least 10,000 from the abundance of hydrogen and helium. And this is a sobering note when you remember that we and essentially our entire planet is made up mostly of these trace leftover materials. Astronomers tend to call anything that is heavier than lithium, so anything past the first 3 or 4 elements, metals. Carbon is not a metal in the chemical sense of the word, but in astronomy, heavier elements are all called metals. So we say that the mass of the solar system and the mass of the universe essentially has 2% metals. But mostly, it's a world of hydrogen and helium. That's our quick survey. This raises many questions. I've listed some of them here, and we'll try to see how many of them we can answer and how many more we can raise as we get into more detail. Why are all the planet orbits circular? Why are they all in a plane? Why are the comet orbits neither circular nor in a plane? Why are all the planets and the large moons spherical objects? And if so, why are the asteroids not? Why are there 2 kinds of different planets? Why are there inner planets of one kind and outer planets of a completely different species of objects? Why aren't the asteroids a planet? There's clearly stuff there. There's room between Mars and Jupiter. Why didn't a planet form there? Why didn't asteroid belts form elsewhere? Why did the rest of the solar system coalesce into planets? This is not a science question, but it's always asked. What happened to Pluto to get it demoted from planet to dwarf planet? What's a dwarf planet anyway? What are rings? Why does Saturn come equipped with these brilliant special rings? What made all the craters? Where did it go? Is it coming back? Are we about to get hit with some big impact? Remember, we did our homework last week and we saw that this can be a significant event. Why do comets sometimes leave their comfortable orbits out in the Kuiper belt or in the Oort cloud and come diving into the solar system? Why do some asteroids move from the asteroid belt into orbits that bring them very near Earth? We keep hearing of near-Earth asteroids and their potential for collisions. And if orbits can change, if something can move from a comfortable orbit out in the Oort cloud and come crashing into the solar system, will the planets' orbits change? Will the solar system remain in its current configuration? Have planetary orbits changed? Was the solar system always the way it is now? And underlying all of this, the question of where did all this come from and when did that happen? And we'll find that starting from the end, in fact, is the way we're going to go. In the next clip, we're going to figure out when it started, and from that we'll try to go on to how it started, and that will try to generate as many answers as we can to all of these questions.